Solve for problem 28 from chapter 8 using figure 8-83. So on that figure, we have a circuit that looks like this. We have a current generator with I of 12 amp connected to a circuit that is laid out in this manner. Okay, and we have point A and B right here, which will be part of the solution domain in terms of VAB. We have an R4 here that is of 4 ohms. We have an E that is of 16 volts. We have R3 over here, which is of 10 ohms. We have R2, which has 6 ohms. And finally here, R1 has 2 ohms. Okay. We're tasked to use mesh analysis to solve, well, let me put out the page here, and that's problem 28, to solve for I2, which they suggested I2 is heading in this direction. That is the current going through R2. So they want the solution for I2. And as I mentioned before, they want the voltage VAB right here. Okay. Now that they are mentioning the mesh analysis, let's look at how this can be done. Let me redraw the circuit even bigger and actually go ahead and do the actual equation, loop equations that would come out of that. Okay? So the bigger it is, the better. And that's what you should do to solve a problem of this nature. Take your time, get another piece of paper, redraw the circuits, and at this stage just put I, R2, R1, R3, E, and R4 as we speak here. So what we want, our mesh analysis requires that you do loop currents in this manner. Now you could do it clockwise or counterclockwise, just stay consistent. Let's call this one I1 for loop 1. Let's call this one I2 for loop 2. And let's call this one I3 for loop 3. Okay? Now, these are going to evaluate branch currents. These, so in other words, like let's say the current going through R1 will be a combination of I1, I2. The current that's going through here is the same. So I1 technically is I. Okay? How about I3? Well, I3 again is based on this, the same current going through the generator E and R4. Our point A and B are still here. Nothing has changed. Okay? However, for the resistor R3, that would be a combination of I2, I3. So to implement this, go ahead and assume that this is the actual current direction that you will use to create your equations as we move forward to solve for this problem. Now, your equations are going to be based on voltages. You're going to apply Kirchhoff Law eventually, okay? But here, let's suppose you have a current going this way. So that means the voltage drop against R1, as seen by I1, would be in this direction. So you would have a positive here and a negative pole here. How about I2? Well, that means the voltage drop will be in this direction. which means this is positive and this one is negative. Okay? How about this one? Well, since you have I1 going in this way, you will have this one positive, negative here, which means your voltage drop technically is going this way. Now, these lines that I'm drawing right here are voltage drops, not current direction, based on these arbitrary current clockwise direction that I picked. Okay? So how about here? Again, voltage drop will be in this direction, which means as seen from here will be this way. How about for loop I3? Same thing. So you will have a positive here, negative here. As seen, voltage drop will be here. This one you have no choice. It will be this way. So this means this is the positive, this is negative. How about here? Again, voltage drop will be always against current when you're dealing with a resistor, right? So you have plus and minus here. Fantastic. Now let's go ahead and talk about I1's loop. Well, that one means I1 equals I. No questions whatsoever. If you have a loop going this way, you have a current generator going this way. Actually, because they're in the opposite direction, I would clearly state it's minus I. Okay? So I have to be really, really careful here because notice that I is going in this direction, and my selection for my arbitrary selection was a clockwise direction. So in that case, I1 will be equal to minus I. Now, had I gone counterclockwise, then I1 would be I. However, the configuration here will have changed, and it would have compensated for the values to actually, at the end, find their correct results. So no matter which direction you pick, just stay consistent. That's the key here. So based on these directions that I picked, so I came to the conclusion that I1 is equal to I. Okay, that's a branch current here. So, okay, right? So we're going to leave this one alone now. We're going to go loop. We're going to call this one loop 2 and loop 3. Okay, so we're going to go to each one and analyze what goes on in there. Okay, for the sake of space, I'm not sure if I want to do this below here or go to the side here. Let's go over here to this side. Loop 2, right? Okay, so this one here was from loop 1. So just to make sure you understand where that came from. All right, so we're at loop 2. And we're going to apply Kirchhoff Law. Okay, so starting, let's say, from this point right here, and we're going to go around. So we're going to go around and evaluate the voltage drops, and we're going to all make them equal to 0. Obviously, that is what happens with voltage drops within a specific loop, right? So, so for loop 2, we know that the voltage drop that we're seeing from this end will be the minus VR1, right? So notice the plus here and the minus. However, this is a composite of the two here. So if it was simply I2, that would have been minus I2R1, right? It would have been something like this, minus I2R1. Except we have a little problem. You still have loop 1. You have to take that into consideration, okay? And notice that the voltage drop on the other end is pointing up in the same direction as you're looping I2. So in that case, you're going to have to write plus I1 R1. So this combination here is really what's going on at this branch right here, between here and here. Okay? So we keep moving. All right, so we take it now and we get to this resistor, R2. And what do we have there? Well, that would be I2 times R2. That would be I2 times R2. Now we run into the issue that we ran into with R1. The same situation will be with R3. So you have a voltage drop here on this, vis-a-vis this loop here, that's opposite to the arbitrary current direction that I picked. Fine. So that would be a minus I2 R3. However, you know it's also plus, since the voltage drop in loop 3 is going the other way, and it has an effect on the total current, right, going through R3. That would be I3R. So let me take an eraser here for a second. Just move this around. We have I here, so I'm just going to write I right here. And that would be I3 R3. And all of this equal to 0. Okay, so that's the basic Kirchhoff law there. How about loop 2? Loop 3 in our case, right? So we've resolved for loop 2. Now we're going to do loop 3. Okay, for loop 3, what you need, again, is start, let's say here, and go around, right? And go clockwise. So in our case, we have a situation with the R3, which is a composite as well. And let's start with minus I3, R3. And notice now you need to do a plus I2, R3. Since this one is heading in the same direction as our loop. Remember for I3, this was opposite, right? So that's important here, and we're reflecting it right here. Next, minus E, since it will be opposite, and then minus I3, R4. Again, equals 0. Fantastic. So now we can group everything, and we can see we have two equations with actually two unknowns, I2 and I3. Okay? So let me regroup them over here on this stage right here. So I'm trying to use this paper as efficiently as I can. And I'm going to do it right here. So loop 2 again. Okay? And what I'm going to do is pull and put all constants on the right-hand side of the equal sign and all variables on the left-hand side of the equal sign. And so I'm going to go ahead and factor in minus I2, for example. And that would be R1 plus R2. Okay? And then what else? Well, how about I1? No, I1 is a constant. We know that I1 is minus I, right? So that's not a problem. So we'll handle that in a minute. So first, let me just go ahead and continue with I3 here. I'm missing a component for I2. So let's fix that. So we have R2 plus R3. Okay. Okay. This is a source of error here, as you can you notice. So I'm just going to check out my I2s here just to make sure that is what I'm doing right there. This is where I got these from. Okay. All right. And then we're going to do the final one, which is I3 plus I3 R3. And I'm going to move the other one to the other side. That would have been minus I1 R1, right? So it would have been minus I1 R1. Now we know that minus I1 will be I. So that's equal to I times R1. Right? We've established that right here. Okay. And we know this is a constant since we know that our current generator here, what was it, 12 amp, right? So this generated 12 amp. So we know it will be 12 times R1, right? So that's a constant. So it will be on the right-hand side of this equation, okay? The key here is I am organizing my variables and their coefficients in a specific pattern with which I can use, or from which I could use a matrix to solve this problem. So let's go ahead and look at loop 3. And same thing, we're gonna put I2 on this end, so we know we have I2 times R3, and then we could factor in the I3. In our case, we'll do minus. Let's factor in the minus I3. So I'm gonna go ahead and do a minus I3 times R3 plus R4. And again, these came out right here and right here. Does that make sense? And we've taken care of this one. Now, that would be equal to E. So move the E, which is a constant, over to this side, okay? Fantastic. So do we have a pattern? And the answer is yes. We have I2, I3, we have I2, I3. Now we could put up a system of equation at 2 by 2 and solve accordingly, okay? Let's look at this loop here and put all our coefficients together, right? So we can add all these up right here to see what values we're going to end up with. So again, let me just draw a line here, and I'm going to do loop 2 again, and this one minus I2, and we're going to put some values right here. So what do we have? R1 is 2, R2 is 6, R3 is 10. So I'm thinking 18. Yeah. So again, R1, 2, R2, 6. So that's 8. So that's 8 plus R3, 10. That's 18 ohms. Fantastic. So how about this component right here? So we have I3. Now, very important that you pay attention to your signs, okay? And stay consistent with that. That's, again, a source of errors whenever you're analyzing a circuit of this nature. So what is R3? That's 10. Right? So we know we're multiplying I2 by 18. We're multiplying I3 by that. And now we're left with I times R1. So that's 12 times 12. 2 times 12, right? So what is that, 24? Fantastic. So that's loop 2. So how about loop 3? Okay, so we're going to do the same thing with loop 3. We're going to put some values, right? So I have plus I2, right? So just leave it as I2, times R3, which is times 10. And then minus I3, right, times R3 plus R4. So what do we have? We have 10 and 4. That would be a 14. Agreed? And what do we have now? Equals to E, and E happened to be 16. So we can put that over here. Fantastic. So what is our system of equation going to look like, right? So what you have is something like this. What do we have? Minus 18, 10, 10, and minus 14. Okay, so we know this is vis-a-vis I2 and I3. So these are what we're solving for. Okay, equals to 24 and 16 over here in this order. And we want to solve for I2 and I3. Okay? Once we solve for I2 and I3, we can deduce from that what the I2 is supposed to be here in what direction. And we will be able to solve for VAB using I3. Okay? Since I3 will be the branch current going through R4 anyway. All right, so the key here is to solve for this system of equations. So maybe the determinant will be a good start. So determinant. Let's hope I spelled it correctly, right? So the determinant for this, right? You can take your, just as a reminder, your minus 18 here, your 10, and minus 14, and you're going to cross multiply in this manner. Except you're going to subtract the second member here. So you're going to subtract this part right here. So that's going to be equal to minus 18 times minus 14, right? Okay. So you're going to multiply these two together right here. Right? So we're multiplying these two together minus, again, the multiplication of 10 times 10, right? So what do we get here? So let me just I have a little cheap calculator here. I just want to go quickly here. So I have 18 times 14. That's 252. Now that is a minus. So minus and minus. That is a plus, I'm sorry. Plus 252 minus 100, right? All right, so what is that? 152. That's for the determinant. Okay, so that's going to be at the denominator for figuring out I2 or I3. So now let's go ahead and figure out, let's say, I2. Right? To do I2, what you need to do is replace the columns for I2 with 24 and 16. Since I2 is the first column, leave this one here, 10 and minus 14, right? And divide everything by the determinant, which happens to be 152. Okay, so what is that? So we have minus 14 times 24, right? So you have these elements here. Again, same technique, cross multiply, minus 16 times 10, right? So times 160, or subtract minus 160 over there, so over this. So again, for my calculator here, so I have a 14 times 24 that is equal to minus 336 minus 160 divided by 152. Okay, so let me just go ahead and do this. Divided by 152. That gives me a 3.26 amps. 3.26 amps. Okay. All right, so can we solve for I3? Same thing. We'll do I3, except this time you're going to leave your minus 18 here, your 10 over here. Replace the columns of I3 with this, okay? Everything divided by 152. Okay, so we cross multiply, so that would be a minus 18 times 16 minus 10 times 24, everything divided by 152. So we're going to do it partially here. So what is it? 18 times 16, so that's minus 288, 288, minus 240, divided by 152. So, by the way, this here is a minus. Let's not forget that because we've got a minus right here, minus, minus. Okay. All right, so we have minus 288, minus 240, divided by 152. So that is, again, minus 3.47 amp. Okay, so I'm staying at two decimal points in terms of precision. And again, I have a minus and a minus. That tells me the current is heading the other way, okay? But that's fine for now. So let's go ahead and figure out what I2 is, or IR2, right? So we want to know what is this truly, what is this I2 here, right? So based on the fact that I said I2 is heading in this direction, right? From my, when I started with the loop, having obtained a negative value means truly the current is heading in the way they assumed in the textbook. So that is correct. So this implies that I2 itself, the real I2 right here, is heading in this direction, and it is equal to 3.26 amp. Okay. How about VAB? Well, seeing the current direction, negative, and I was going this way, so that means the actual current, I3, is heading this way, which means VAB is really negative, and it should be heading this way, okay? So this implies that VAB is going to be equal to minus I3, or in my case, absolute value of I3, right? So, so what is I3? So my 3.46, right? So my minus 3.47, right? Times R4, which happens to be 4, right? So VAB is going to be equal to, so let me just go ahead and do this. So 3.47 times 4, right? So that's minus 10 volts, 10.4 volts. Where's my pen? Here you go. Minus 10.4 volts. A slight error here. Well, it's not slight. That is a big error. I made a mistake here, so let me just see if I can delete this. Here's my eraser. Okay. All right, so 3.47 times 4 is actually minus 13.88. Okay, on that, we should be done. So we have our voltage here, and we have I2 here, based on the direction the problem started with. Thank you.